In this lecture, we are going to look at a Colab notebook that does transfer learning without data augmentation. This lecture is going to walk you through a prepared Colab notebook, although a very good exercise, which I always recommend, is once you know how this is done, to try and recreate it yourself with as few references as possible. As usual, you can look at the title of the notebook to determine what notebook we are currently looking at. And this notebook is called PyTorch Transfer Learning Fast. So our main goal in this script is to see if we pre-compute the features. A, will training be faster? And B, will we get an unacceptable reduction in accuracy? I'll assume that in this lecture you've already seen the code that does transfer learning with data augmentation, so I'm not going to explain any of the lines that I've already explained. So at the top, everything is the same as before. Same imports, same data, same process to move the data into the folders which are structured the right way for the image folder dataset object. Okay, so when we get to the transforms, you'll notice that we only have one. Why do we only need one? Well, since we're not going to do any data augmentation, we can apply the same transformations to both the train and test set. And these are all non-data augmentation transformations. So next we create our image folder objects. Next we create our data loader objects. Next I grab the pre-trained model with pre-trained equals true. So the next part is also new. Since the VGG operation is separate from the rest of the network, we can define a separate model for it. So I'll define a class called VGG features. In the constructor, the only thing I need to do is save the VGG model. In the forward function, I take X and I pass it through the different parts of the VGG one at a time until right before the final classifier. At that point, I just flatten and then return. Next, I instantiate this class and I call it VGGF. Next, as a sanity check, just to make sure this works, we pass in a random input. The output is shape 1 by 25,088, so it works. Next, we're going to transform our data using the feature transformer that we just instantiated. So first, we need to find the length of each dataset. Luckily, we can use the len function on the dataset objects. So we have ntrain 3000 and ntest 1000. Next, we're going to grab D, the feature dimensionality. This is the size of the output of the VGG transformer, which is equal to 25,088. Next, we're going to work on creating our tabular dataset, consisting of transformed features from the original data. Once we have this, we no longer have to work with the original dataset. So we're going to start by instantiating empty arrays to store xtrain, ytrain, xtest, and ytest. Next, we're going to set the device to the GPU and move the feature transformer to the GPU. Next, we're going to populate xtrain and ytrain. We can do this by looping over the train dataset. So on each iteration, we start by moving the inputs to the GPU. It's not necessary to move the targets to the GPU because we only want to make a prediction with the model. Next, we get the output by passing the inputs through VGGF. Next, we get the size of the output. Note that this is not equal to the batch size, since the number of samples may not divide evenly into the batch size. So the final batch is less than or equal to the batch size. Next, we assign the features and the targets to xtrain and ytrain at the current index I. Then we increment I by the current batch size and go to the next iteration of the loop. So since we print I on each iteration, we can confirm that the number of samples in our new dataset is equal to the original number of images. Alright, so we can see that the final value of I is 3000, which is the correct number of samples. Next, we do the same thing for xtest and ytest. So one thing that's interesting to check is the min and the max of the feature values. As you can see, the max in xtrain is about 62, which should seem weird to you because you should expect values in a neural network to be somewhat normalized. Since we're using a ReLU activation, the minimum value was 0. So anyway, since the data is at this weird scale, we're going to use a standard scalar object to transform it. So we'll call the scaled data xtrain2 and xtest2. Now, because the next step is to do logistic regression, there's no actual reason we need to use PyTorch. In fact, we can just use the logistic regression that's built into scikit-learn. So let's do that. As usual, it's just fit and predict, which I've taught you for free in the past, so everybody knows this. And as you can see, we do very well. Just as well as when we did use data augmentation, in fact. So maybe data augmentation wasn't so useful in this instance. Next, we're going to complete this script by doing transfer learning the usual way, which is to use the same library for the classifier. So let's start by creating a linear model, and the rest of these steps you've seen before. So we move the model to the GPU, create the loss and optimizer, make some tensor dataset objects, create the data loaders, define the training function, call the training function, plot the loss per iteration, and calculate the accuracy. And so we end up with pretty much the same result. Also important, notice how much faster this is. With data augmentation, each epoch takes about 40 seconds. Without data augmentation, each epoch is nearly instant, about 0.2 seconds. So that's a 200x speedup by not using data augmentation and not having to go through the pre-trained network on each pass.